Hello, I'm Bjarne Olesen, President of ASHRAE. Welcome to today's webcast, Making Energy Efficiency a Reality. Delivering meaningful energy efficiency in buildings often requires dispelling the myth about building products, performance, and solutions. Our presenters will address the myth and present the facts they discover through real-life experiences. They'll also share a holistic approach to assessing a building and its systems based on varying climates and economies. You will learn strategies and policies that take an in-depth review of efficiency goals and learn how to achieve optimum energy performance in commercial and high-rise residential buildings across the globe. Thank you for joining us today. I look forward to hearing from our presenters and from you during the question and answer portion of the webcast. So let's get started.
Hello and welcome to ASHRAE's 2018 webcast, Making Energy Efficiency a Reality, brought to you by the Chapter Technology Transfer Committee. I'm your host, Jennifer Gladstone. On behalf of ASHRAE, I'd like to welcome all our viewers and thank you for joining us. ASHRAE is a global society advancing human well-being through sustainable technology for the built environment. The society and its members focus on building systems, energy efficiency, indoor air quality, refrigeration, and sustainability within the industry. Our vision is to be the global leader, the foremost source of technical and educational information, and the primary provider of opportunity for professional growth in the arts and sciences of heating, ventilating, air conditioning, and refrigerating. For more information about ASHRAE, visit ashrae.org. Now let's meet our panel for today's webcast. Chris Mathis is president of MC², Mathis Consulting Company in Asheville, North Carolina. With a Master of Science in Architecture Studies from MIT, Chris has spent over 35 years focusing on the role of buildings and how they perform. Chris has worked with standards and code development internationally and with IECC, IGCC, U.S. Energy Performance Rating and Labeling Systems, and has worked to help shape several ASHRAE standards such as 90.1, 90.2, and 186.1. Chris is also an ASHRAE Distinguished Lecturer. As president of Mathis Consulting Company, Chris focuses on working with strategically aligned clients, leveraging knowledge and understanding to improve buildings, building products, and the codes and standards that govern them. Chris, it's great to have you for another ASHRAE webcast.
Thank you. Glad to be here.
Great. Tom Durkin is senior partner at Sims Durkin Associates in Indianapolis, Indiana. Recognized as an innovative and creative engineer throughout the Midwest, Tom's designs for buildings and systems are proven to be energy efficient and cost effective. He's been a contributor to the U.S. Department of Energy and designed the first Energy Star School HVAC system in the Midwest. In 1998, Tom presented one of his innovative systems to the United States Congress. Tom has either invented or pioneered the implementation of 12 distinct HVAC innovations in which they save energy and reduce pollution. His work has won 2 ASHRAE Technology Awards. At Sims Durkin Associates, Tom oversees all aspects of the SDA mechanical design, and their highly qualified team of engineers is committed to providing innovative engineering systems that save on operating costs, meet the budget, and match the architectural design. Tom, welcome.
Thank you.
And Mark Frankel is the technical director for the New Buildings Institute in Portland, Oregon. NBI develops programs, policy, training, and research on high-performance buildings and energy efficiency for organizations all over the U.S. Currently, Mark is involved in national coalitions to improve building performance feedback, market adoption strategies for net zero energy, and development and implementation of innovative codes and policies focused on building performance outcome and benchmarking. He's been consulting on energy efficiency and sustainable design for over 25 years and has consulted on hundreds of capital projects ranging in scale from single and multifamily residential projects to large commercial buildings and portfolio strategies. He's a lead fellow and a licensed architect. And Mark, it's great to see you.
Thank you for having me.
All right, this is what's coming up in part one of our webcast. An overview from our panelists on today's subject matter, a presentation and case study on why building energy efficiency must be considered holistically, a presentation and case study on deep energy efficiency. We'll also have 2 roundtable discussions, and we'll hear from you, our viewing audience, in our first question and answer segment. If you have a question for our panel, please use the interface on your screen to submit it at any time during the webcast. And now Chris, Tom, and Mark will provide us with an overview of today's show and the challenges we face trying to deliver energy efficiency. Gentlemen?
Thank you, Jennifer. As ASHRAE members, we often forget our shared mission to serve humanity and promote a sustainable world. It's easy to get caught up in our day-to-day activities and forget that what we do every day as engineers, architects, and building science professionals is essential to the human condition and firmly rooted in important service to all humanity. What we do is important. Today, we will get some reminders to provide some scale to the importance of buildings in the United States and worldwide. While we'll be focusing on building energy performance, we'll also be reminded about how that energy performance is intimately connected to other critical aspects of overall building performance, from indoor environmental quality to human comfort and health. We will consider building energy performance in its broader context, connected to available resources, critical energy, and environmental policy decisions. And we will look at these connections with a renewed consideration of a building's expected service life. We often default to the expectation that technology will offer the solution to all these challenges and responsibilities. And all too often, we focus on the technological solutions that we happen to offer. But we know that all of these diverse parts and pieces and technologies must work properly together to deliver the energy performance, comfort, and environmental quality we expect. And they must work for a long time, often over 100 years. With these concepts in mind, we'll look at building energy efficiency in some new ways. We'll talk about the need to better engage with everyone involved in critical building decisions, from architects to product suppliers, from building inspectors and operators to owners and regulators and policymakers. We'll discuss things that may be out of our normal comfort zone regarding valuing better building energy performance, such as how do we shape the codes and regulations governing delivered building performance, and what are our responsibilities regarding the performance of people's homes, from single-family to high-rise residential structures. And we will be reminded of one of the biggest performance challenges we face, the projects that are most challenging and that demand the very best of our skills, existing buildings. We'll share some case studies demonstrating how addressing the needs of existing buildings can have multiple derivative benefits to all. And we'll end with a discussion of our roles and responsibilities as building performance communicators. How do we change? How do we challenge the status quo interaction with others on our projects? How do we effectively challenge the common approach of merely throwing the next new technology at problems, especially problems that we know require more systems thinking? And how do we better communicate and deliver on our important shared mission to serve humanity and promote a sustainable world?
There is a distinction, however subtle, between energy efficiency and energy conservation. Conservation is using less energy. Efficiency is using it more productively. Our objectives as ASHRAE and as global citizens should be both. As a designer, making energy efficiency a reality means that after a project is built, the systems are delivering the potential that we sought with zero compromises in indoor environmental quality, occupant comfort, or humidity control. One of my adages for our K-12 projects is this: good design plus good operation equals more money for kids. And good design isn't just an efficient system or efficient components. Good design is how effectively everything is woven together into a coherent package. Good design is the judicious application of technology, recognizing that even the best ideas can be poorly applied, and also recognizing that we engineers can sometimes overcomplicate things to everyone's detriment. Good design means that we have coordinated our sizing to the building components that our architects, brothers and sisters have given us, and that we've had the collaborative exchanges with them necessary to make the construction budget and the energy budget work. Good operation means that the temperature control contractor, the commissioning authority, and the building operators understand and can execute our concepts and possibly improve on them. And just like in real estate, where the three most important factors are location, location, and location, the important factors in efficient operation are schedule, schedule, and schedule. The closer we can match operation to occupancy, the more efficient we'll be. Now, in my part of the world, where we air condition for humidity control and comfort, matching ventilation to occupancy is key to efficient scheduling. And being the gray head in the office means that I make the rules, and one of them is Tom's 50-70-95 axiom. Fresh air, as dictated by ASHRAE Standard 62.1, is a necessary component for a healthy and effective living, learning, working environment. But fresh air is about 50% of the cooling cost, 70% of the heating cost, and 95% of the potential humidity problems. 4 excellent reasons to ventilate effectively, but only when the kids are there. And finally, ASHRAE has done an excellent job of helping us make it a reality with standards 90.1 and 189.1. They have literally hundreds of what I call nuggets of high-performance design. That's design, construction, and operation ideas that make it easier to weave that coherent and efficient package.
Although we measure energy efficiency at the building level, efforts to improve efficiency in buildings have long been tied to larger policy goals. Over the course of nearly 50 years of energy efficiency progress, both the goals and the technical strategies to achieve building performance improvements have changed significantly. In this presentation, we will discuss the evolution of policy goals and market practice, and how these have together impacted the deployment of energy efficiency strategies in buildings. Energy use in buildings represents about 40% of total energy use in North America. This makes the building sector a major consumer of energy supplies and a critical component of larger energy policy goals. Since the 1970s, government entities have adopted specific policies to encourage improvements in the building stock as a means to reduce energy use. The first efforts by policymakers to address building energy performance were driven by sudden disruptions in the U.S. energy supplies by OPEC in the 1970s. Subsequent policy motivations evolved to require least cost resource planning for new electric supplies, and more recently into efforts to reduce the greenhouse gas impacts of the building sector. The mechanisms by which policymakers impact building performance have long been tied to utility incentive programs for energy efficiency in new and existing buildings, and to mandatory building energy codes that require the incorporation of building energy efficiency features in building design. Over the past 5 decades, government agencies and utilities in the U.S. have invested billions of dollars in research and deployment to support program and technical development of new strategies to reduce energy use in the building stock. Utilities must demonstrate to regulators that they are investing in the most cost-effective resources to meet new electricity loads. Energy efficiency has been demonstrated over and over again to be one of the cheapest ways to secure new power supplies. Likewise, research suggests that building energy efficiency programs are likely to represent one of the least expensive strategies to achieve greenhouse gas emission reductions as well. The success of these programs in some regions to help manage utility load growth has been stunning. But we have also recognized significant limits to conventional widget-based approaches to building energy efficiency. New technologies and market structures are forcing a new, more integrated approach to how we deploy energy efficiency programs and strategies in the market, as policymakers set aggressive new goals for performance improvement in the building sector. To understand why the energy efficiency market is changing, we have to recognize how market practice, energy efficiency incentives, and building codes are interrelated. The goal of incentive programs is to encourage potential market leaders to adopt progressive energy efficiency strategies above and beyond standard practice. As more and more projects adopt these strategies, the market demonstrates that advancements have been made toward energy efficiency, and these strategies can then be incorporated into more stringent energy code requirements, pushing standard practice forward. Incentives adjust accordingly to encourage the adoption of new technologies and design strategies to further increase building performance. Taken as a whole, this process is referred to as market transformation in the building industry. In the past, the process was slow, with energy codes demonstrating steady but slow progress toward reduced building energy use. More recently, the rapid growth in the number of projects successfully targeting deep efficiency and Z&E performance across the building spectrum has demonstrated that major improvements in building performance are possible. These improvements are not just the result of improved building physical features, but also come from new approaches to long-term operating strategies and tenant engagement. And the proliferation of renewable energy installations has completely changed the way buildings interact with the utility grid, significantly altering the financial equation that has traditionally supported utility incentive programs. Policymakers have been quick to recognize that these deep efficiency improvements can support more aggressive greenhouse gas reduction goals, such as the 2030 Challenge and the Paris Climate Accord. This has significantly accelerated the pace of change in building code requirements. These changes have occurred so rapidly that many conventional utility incentive programs are underwater, meaning that they no longer represent industry-leading practices that exceed energy code requirements. Today, we will discuss how these factors will soon play out as new approaches to energy efficiency programs across the building industry. Jennifer?
Thanks, gentlemen. And Chris, don't go too far away. Understanding why building energy efficiency must be considered holistically is easier said than done. Chris will now walk us through the basics of energy efficiency in this presentation, The Complete Building, Delivered Performance Through More Holistic Thinking. Chris, it's all yours.
We've often heard that the whole is greater than the sum of its parts. So it is for buildings. We assemble many diverse parts, from envelope parts like walls, floors, roofs, fenestration, air barriers. We often treat many important building decisions in silos. We rely on many HVAC parts to work together. HVAC decisions often take place in silos too. Similarly with lighting and controls. All share the goal of delivered whole building performance. But are we focusing on the whole or just our silo? What about the rest of the silo? All these different components are then assembled in hopes that it all works together as expected. Building enclosures that protect against the forces of nature, sun, wind, rain, sleet, snow, and systems that deliver on all the different performance expectations. So how do we get individuals focused on their particular silo to work more holistically to deliver whole building performance, from energy, power, water, environmental quality, daylight, health, carbon, safety, comfort? And we expect that performance to last. But for how long? Buildings typically last over 100 years. So we often get involved in establishing long-term operational and maintenance procedures, hoping to deliver on those performance expectations for as long as possible. As professionals in building performance, we may approach all projects with this holistic thinking in mind. But sadly, most building professionals have failed to fully convey the importance of their buildings and their energy use. This importance far exceeds monthly energy bills. We need to do a better job teaching and conveying the importance of buildings. Let's look at some indicators of this importance. And while we focus primarily on U.S. data, similar trends in building performance can be seen worldwide. You can think of the U.S. energy appetite as about 100 quads. Most ASHRAE webcasts have drawn attention to the fact that buildings are the single biggest energy use sector in the U.S. This energy demand is fairly evenly split between residential and commercial buildings, with homes demanding a bit more than the commercial sector. This energy demand is defined by our insatiable appetite for electricity. And while the demand profile for the rest of the world may look a bit different, you can see that the rest of the world will soon need as much energy for their buildings as the entire U.S. energy consumption today. This appetite is currently fed mostly by finite resources, fossil fuels, and projections on the future do not look dramatically different. When we look more closely at the energy demand of our homes and commercial buildings, we note some commonalities. First, note that most of our commercial buildings were built before 2003. Over 60% of them were built before 1990. We built most of the commercial buildings in the U.S. between 1950 and 1980. What characteristics do these buildings have in common? Little to no insulation in the walls, little to no insulation in the roofs, terrible windows, leak-like sieves, out-of-date HVAC systems, and lighting. If we consider residential buildings, they have about the same age distribution and the same energy performance challenges. These existing residential and commercial buildings are like the big gorilla in the corner, consuming precious energy resources at an alarming rate compared to minimum code buildings today. In fact, today's minimum code for commercial buildings, ASHRAE 90.1/2016, shows an almost 50% reduction in code-regulated energy use compared to a code minimum building in 1975. It's important to remember that these minimum code improvements do not account for the increased energy demand for all the gadgets, the computers and the cell phones and other things we plug in every day, those non-regulated loads. So we're doing some things right. We've made advances, better building envelopes, better HVAC systems, better lighting, better controls, all in a time of ever-increasing demand. Let's put some additional scale to the challenges and opportunities we face. In a good year, we'll build about 1 million new homes in the United States. Compare that to 130 million existing homes, most of them over 40 years old. So when we consider our mission in the context of these energy trends and building data, we have to ask, what is our responsibility? Worldwide, similar trends exist. Ever more energy demand, serving more and more people, all demanding and needing energy. These trends are complicated by the fact that we're expecting more from our buildings. In the U.S., we spend almost 94% of our time indoors, and we expect our buildings to be energy efficient and safe and durable, have better indoor environmental quality, be healthy, be resilient, be green, be sustainable, and have many other attributes. And we expect them to deliver on these performance expectations for their life. And with all this ever-increasing demand, what can we do to better address these growing needs? Do we have the available fuels to provide electricity, heating, cooling, power, and water to everyone? What can and should we be doing to promote better building performance in the face of this ever-increasing need? And how long will the performance truly last? Are we addressing all of the essential human needs? Are we delivering on our mission to serve humanity and promote a sustainable world? All too often, we seek to apply technology, whatever the latest tools offer, to try to address the challenges we face, solve the problems we're trying to solve. It's our nature to use the tools we're trying to sell. In building energy performance, our solutions all too often involve throwing horsepower or tonnage or watts at a problem. How often do we step back and truly conduct a root cause analysis prior to applying technology? Does the real problem lie in an area outside of our current technological toolbox? There are many different professions and skills necessary to deliver buildings that begin to meet all of our diverse performance expectations. Architects and engineers, owners and operators, finance and insurance, code officials and lighting designers, and many more. Each bring unique tools and capabilities to the job site. It may seem uncomfortable at first, not jumping to the latest tech solution in our toolbox. This is especially true when we're challenged to think about basic energy efficiency. Some of these important aspects of building energy performance have a very long life. Building envelope measures in particular. It's hard to get excited about wall or roof insulation or window performance or air barrier performance when what we'd like to do is get to the topic of our latest new tech. Everyone around the table wants to get to their preferred solutions. But when we pause and step back and begin to think more holistically, we soon realize that all of the various professionals around the table share a common set of objectives. Everyone wants a successful building project, a building that works. All too often we encounter problems in long-lived building decisions. For example, air leakage, envelope thermal deficiencies, inadequate materials. Sometimes the messages are pretty simple. And sometimes we have to question fundamental design decisions, especially when the problems are repeated. The good news is that we know where a lot of these common problems exist. Today, we will share what can be achieved when we get out of our comfort zone and really try to engage in holistic thinking and communication. We will challenge everyone to break out of their technological silos, remembering the basic components of delivered building performance. These techniques require something we can all benefit from: better communications. Good communication is often the key that unlocks better decisions, better solutions, the key to a project's long-term success. These decisions are going to be with us for a long time.
Thank you, Chris. So how does this play out in the real world? Well, Tom Durkin is here to provide one example of energy efficiency in action in this case study on Manchester University. Tom?
Thank you. Now we should clarify that we're talking about holes with a WH and not holes like in the knees of your jeans. The word holistic means concerned about holes and recognizing the interdependency of the several parts. Now there's several possible ways of looking at holistic energy efficiency. The most obvious is the interdependency of the building envelope and lighting to the HVAC sizing, which is a recurring theme of today's webinar. But I think opportunities for broader holistic energy efficiency can be found on most higher education or hospital campuses and in multifamily occupancies if we look hard enough. And what I'm suggesting is that when we get a project opportunity, let's not look at it with blinders on. Holistic energy efficiency works best when we have wide peripheral vision. Let's recognize all of the potential interdependencies of a project. Sometimes they might not be very obvious. The one I want to highlight today is the Manchester University Academic Center. This is the north end of the main quad at Manchester. The project was an addition to and the renovation of the old 1950s vintage Hull Kintner into their new academic center. There are utility tunnels connecting all three buildings. Steam comes from a power plant to HK in the auditorium. The new science building has its own boilers, which was phase one of a planned decentralization of campus heating. All three buildings need reheat for summer humidity control, but it was not available at HK or the auditorium because the campus steam system was off from April through September. Chilled water mains connect all three buildings, but the campus loop was short of capacity. The university considered two approaches to the academic center project: a straightforward, standalone approach and the holistic approach that we were advocating. The holistic approach would address the immediate needs, but it would also address the summer humidity concerns at the auditorium, and it would advance the campus decentralized heating plan relative to the auditorium. Mechanically, what were the differences? The first was straightforward: boilers and chillers at the academic center. The holistic approach added a heat recovery chiller and a low-temperature condensing boiler at the Science Center and connected all three buildings together with heating water mains. Steam would no longer be required on that end of campus. Now, the construction manager was concerned about the cost implications, and justifiably so. The holistic approach would increase the project cost, but not very much. But if the future master plan dollars for getting the auditorium off-campus steam were included, there was a net decrease in cost, and additional area inside the academic center is now available for academic uses. This is how the new heat recovery chiller at Science Center is piped, connecting to the campus chill water mains ahead of the science building pumps. There is an air-cooled condenser that isn't shown here. The chill water sequences mean that the heat recovery chiller meets the chill water requirements of the academic center. The heat recovery chiller runs to meet the summer hot water requirements for all 3 buildings. The heat recovery chiller runs to meet the campus chill water requirements in wintertime, and with the air-cooled condenser, the heat recovery chiller can run for load if the campus loop is at capacity. The science building had been designed for 180-degree heating water. The other 2 buildings were being designed for 130-degree heating water, both reset based on outside air. Here's a good question. How hot does the heating water at science need to be? Well, it varies, but we would know that if we looked at the control valve position. We want to run the science heating system at the minimum temperature that would maintain the building. It doesn't have to be 180 very often, and if no hot water control valve is more than 90% open, then the water is hot enough. This is how we piped the hot water side with all the equipment in the science building mechanical room. The original science boilers and pumps are on the left, and the new heat recovery chiller, condensing boiler, and pumps that serve both the auditorium and the academic center are on the right. The 2 hot water systems are connected by the lines at the top and the bottom of the schematic. With the holistic approach, we end up with 3 stages of heating for all 3 buildings, and they're arranged by cost. The objective is to minimize the operation of the science high-temperature boiler plant. A good energy conservation measure is always to run the heating system as cool as safely possible, which is easily done if you know the position of the hot water control valves. We don't burn gas unless there's no heat to recover, and we don't run the big boilers unless a condensing boiler running at a much lower temperature cannot keep up. 3 buildings are now heated from the Science Center, which is double the area, and the amount of gas used actually went down 22%. We converted 2 buildings from steam to low-temperature hot water and decommissioned 1,000 feet of steam mains, eliminating about 1.8 million pounds of steam per year. Here's the same results graphed by month. The blue line is the gas used at science by itself before the project. The red line is all 3 buildings after the project. Including the steam no longer used, which isn't shown on the graph, there was a 41% decrease in gas use. 1 month in the middle of winter, we did use more gas than the previous year, but again heating 3 buildings instead of just 1. We did not meter electricity, and clearly electric use at science went up due to the heat recovery chiller and the extra pumps. But it is a legitimate argument to say that the electric increase was minimal because the heat recovery chiller was running to make chilled water that the campus needed and used, and the pumps would have been running anyway, whether they were located in the science building or the academic center.
Thanks, Tom. Well, Tom joins us here on the panel. Let me remind you that if you have a question, please use the interface on your screen to submit it anytime during the webcast. We look forward to hearing from you during the upcoming question and answer segments later in the webcast. And now it is time to turn to our first roundtable. Let's delve deeper into holistic energy efficiency. Gentlemen, are we ready? Let's see, the first question, is energy efficiency the same as building performance? Let's toss this to Mark to start off with.
Thanks. I would say that energy efficiency contributes to building performance when it's part of a well-integrated holistic system that is well-maintained and operated. So it doesn't individually guarantee building performance, but it's part of the package.
Okay.
I would offer that we don't know unless we measure. You know, we need to be doing Energy Star benchmarking or ASHRAE ZQ benchmarking for these buildings, but we really don't know whether, you know, whether it is or whether it isn't without the measurement.
Okay.
And to their point, you know, if we measure, you know, we have this bad habit of taking a perfectly good building and then we put people in it, and then we have to remember that the people have to have comfort conditions met, and measurement is key. And energy efficiency is certainly a key component of that building performance.
Okay, well, why don't we move on to number 2? What are the right questions to ask when we undertake an energy efficiency project? I'm going to turn to Tom for this one.
Well, maybe it's the building owners who should be asking the first questions.
Okay.
And by that I mean that the owners should be doing the asking. They should be hiring engineers who have the experience and the vision to help them create these energy efficient buildings. So that would be one thing.
Okay. Anything to add?
You know, one of the challenges in dealing with building owners is understanding their boundary conditions or helping them understand their boundary conditions. Are they just looking for short-term payback? Or are they making a valued building investment? And, you know, different owners and different projects will have different building priorities.
So communication.
Critical.
With everybody. All right, shall we move on? When planning an efficiency project, what does holistic mean? I think we may have touched on that in some of the presentations, but let's repeat that, Chris, for everyone.
You know, I think everything has to be on the table. You know, holistic, we'd like to think that it's everything, but we may not have all the right people around the table. As in the last question, we may not really understand what the boundary conditions are. Are we making a decision on an appliance that might last 10 years, or are we making a decision on an envelope element that might last 100 years? So we really have to understand those boundary conditions and have everything on the table to be able to think holistically.
Okay. Mark, do you have anything to add?
Energy efficiency isn't a feature, it's part of an integrated system that you have to think of all the things that are affected by that feature and make sure you're addressing all of them when you adopt energy efficiency.
Tom, anything to add? All right, we'll
I'm
move
good.
on. Let's look at question number 4. How does a holistic approach to energy efficiency affect the project cost? And I think with this one we are going to turn to you to start us off.
The real winners are the projects that are less expensive to build and less expensive to operate, more energy efficient. My Manchester was a good example of that there. There is an article in last month's ASHRAE journal about the technology award winner for this year, which was a project on the Western Michigan University campus, I believe. Another example of where the least expensive option was the most efficient. Now, that doesn't happen very often, where we get, you know, those two things coming together, but it can, and but we won't know that unless we really, really try to find those opportunities.
Okay.
Every building scientist around the globe will tell you that buildings are systems and everything has to work together. And Tom's comment about having a wider peripheral vision is really key here. We might try to figure out how we could, you know, take certain things out or save money here or do a value engineering project to try to take some costs out. But by having everything on the table and thinking holistically and thinking about it as a system, we're going to deliver better solutions.
There's also a time dimension, I think, of how long you think about this system for. If you're looking for a 2-year payback, you're going to be looking at a much narrower band of performance than if you think for the long term.
And Chris mentioned value engineering, which is sometimes a bad word in our industry. But value engineering is sometimes we end up having to do just out of necessity. But when we're doing that, we need to make sure that we're not valuing the engineering out of the project. And one other thing about how holistic approaches may affect cost. The Manchester project was the second one of that similar design that I had built. The first one was a project at Indiana University where we designed a base bid without the holistic approach, and we designed the holistic approach. The holistic approach came in, it was $159,000 more, but the energy savings put that at a 2-year plus payback. Now, thankfully, the entire project was under budget, and we were able to build the holistic approach. But unfortunately, had the project not been under budget, you know, we had some pretty good engineering ideas that might not have gotten built otherwise.
Very interesting. Thanks, Tom. All right, so what are the short and long-term implications of bundling efficiency strategies? Mark, you want to start us off?
one way you could look at it is if you pick the low-hanging fruit, you might do that at the expense of the value of the harvest. So you have to really think about the whole set of efficiency measures and attack it as a whole and not just take the most cost-effective things now. You'll never go back to that building if you take away the good stuff at the beginning. You'll never be able to afford it.
Okay.
Yeah, we often say the whole is greater than the sum of the parts. Better insulation, better windows, better roof insulation, better air sealing are going to result in maybe a smaller, more easily controlled HVAC system that delivers greater comfort and greater savings. But you have to think of those things together as a bundle, and you might take out one of those elements and really lose the opportunity that was presented.
Sure, understood. Okay, let's see here. Who needs to be engaged in a successful energy efficiency project, and what happens if they're not? How about you, Mark? What happens?
Well, energy efficiency is a strategy to enable better building efficiency. It doesn't guarantee it alone. So we need training and commitment to long-term operation and maintenance for this strategy to succeed over time. So you can't just think of it as something you're going to buy. It has to be a system you're going to implement and maintain over time.
And we have to have the diversity of people around the table. We're used to certain project tables where, you know, you've got an architect and an engineer and a building owner and maybe the general contractor and the project manager, but there are probably some other people that we might want to think about having around the table. For example, your local code official. Does he or she know what your objectives are for your project? If you engage them early on in the project, they may actually be a critical partner in helping you accomplish those objectives. Your lender, who might really have a first cost focus, but if he understood that your operating costs are going to be dramatically changed as a result of more holistic thinking, you could deliver something that it's of greater value to that lender, maybe lower lending risk.
Okay.
And I would add that in my experience, one of the hardest things to find on a successful energy efficiency project is an owner who really cares. Okay, and I think everybody cares at some level, but to be able to do what Mark is suggesting, you know, that long-term investment there. A good owner can make me look pretty good, or he can make me look pretty average.
We have to do a better job of teaching the economic power of holistic thinking.
Is it just that they're thinking about the bottom line and it's just that final cost? What do they really care about?
I would say too often, yes.
Okay. All right, gentlemen, thank you so much. That brings us to the end of our first roundtable. And now we're going to take you into a concept called deep energy efficiency. I won't steal Tom's thunder, but I will.